Welcome to EDU World Space.
So in this question, we're given some information about an impact with a comet. The comet was observed to be 9 kilometers across, and the observations showed that the debris or the dust released upon this impact with a speed as low as 1 meter per second was able to escape the comet. So assuming a spherical shape to the comet, we're asked to calculate the mass of the comet. And then in part B, we need to show something else. So we are referred to example 12.5. And in example 12.5, a formula is derived for the escape speed of an object. And this is equal to the square root of g 2 gm over r. So we can use this formula, we can reverse engineer it to find what the mass of this comet must be since we were given the escape speed. So we can square both sides of the equation, so that gives us VE squared is equal to 2 gm over r, and then we can multiply both sides of the equation by r and divide by 2g. And so that'll give us a formula for the mass equal to VE squared times r divided by 2g. And so we can just go ahead and sub in the values that we've been given. So 1 meter per second squared for the escape speed. The radius, we were given the diameter, it's 9 kilometers across, so the radius is 4.5 kilometers across, or 4,500 meters. And then we divide by 2 times the gravitational constant. And that will give us a mass for this comet of 3.37 times 10 to the 13 kilograms. So this is the final answer for part A. And then in part B, we are asked to calculate how far from the comet's center will the debris be when it has lost 90% of its initial kinetic energy, and how far will it be when it has lost all of its kinetic energy. So this is really a question about conservation of energy. So basically, in the first part, we want to take 90% of the initial kinetic energy and set that equal to the change in the potential energy. Because as we're losing kinetic energy, that should be converted into potential energy. And so that will allow us to calculate an R value for how far away the debris is. So what I'm going to do is I'm going to take 90% or 0.9 of the initial kinetic energy, and I'm going to set that equal to a delta U, or a change in potential energy. So 0.9 EK will be equal to the final potential energy minus the initial potential energy. And what I'm going to do now is I'm going to actually sub in the formulas that we usually use for these things. So for kinetic energy, 1/2 mv squared. And for potential energy, it's going to be negative G mm over r, where big M is the mass of the comet, small m would be a piece of debris. And I'm going to label this first R RF because this is going to be the final R. And then in the second term, we'll label it RI because this is the initial R. And you can see right away that we can cancel out all of these M's. So that makes things a little bit easier here. Now, on the left-hand side of the equation, we can consolidate this. So 1/2 times 0.9 is going to be 0.45 v squared. We can substitute in G and the mass that we found for the comet. That gives a value of 2,248. And that's going to be RF. RF is what we're trying to find, right? It's the radius that the debris is at when it's lost 90% of its kinetic energy. And then GM over RI, we have all of these values. So the initial radius is just the radius of the comet, right? Because initially the debris is on the surface of the comet. So we would substitute in there 4,500, substitute in G and M, and we get a value of 0.5. And so we can solve this equation for RF. V is just 1, so on the left-hand side, we just have 0.45. We subtract 0.5, so we get 0.05. And then we can multiply by RF and divide by 0.5. So once we do that little rearrangement, we get, sorry, this would be negative. We get negative 2,248 divided by negative 0.05. And so that will give us a radius of 45,000 meters or 45 kilometers. So this is our final answer for the first part of part B. This is how far the comet will, or the debris will be from the comet's center when it's lost 90% of its initial kinetic energy. And then in part 2 of part B, we are asked to find the distance from the comet center when it has lost all of its kinetic energy. Now, this debris is going at 1 meter per second. It's going at the escape speed of the comet. And the escape speed is basically defined as that perfect amount of kinetic energy where it's just enough kinetic energy to get over the hill of, or over the deficit of potential energy that the debris has at the surface of the comet. And so no matter how far away the debris gets from the center of the comet, it's always going to have a little bit of kinetic energy left over, and it's going to keep converting into potential energy forever and ever. Now, if we had a piece of debris with a slightly bigger speed, slightly bigger than the escape velocity, then there would be some distance, some finite distance where, the debris would truly, have escaped all of the kinetic, most of the kinetic energy would be enough to get it over that hill of potential energy. So the answer to the second part of part B is that there really is no distance from the comet surface that the kinetic energy of the debris would be 0. And so the distance at which that happens is basically infinity.